Chain rule, derivative of a composite function. That's really what the chain rule is all about, is a sine of x squared minus 4. So a function with inside a function. And how do we take the derivative of that? And the answer is with the chain rule, which is probably the most widely used differentiation rule in mathematics. It will follow you the rest of the year. Pretty important. That's why we spend 4 days on it. We're not going to spend 4 days on hardly anything. So relating derivatives. The function y equals 6x minus 10, you can factor a 2 out, and it's 3x minus 5. Is the composite of the function y equals 2u and u 3x minus 5? How are the derivatives of these three functions related to each other? So let's write out y equals 6x minus 10. Let's write it as y equals 2 times 3x minus 5. And we'll write y is equal to 2u, where u is 3x minus 5. So that third one, it's the same thing, because we could plug 3x minus 5 into u, run the 2 through, and all of those would end up being 6x minus 10. So dy dx here is 6. Nothing new there. Dy dx here is the chain rule. It's the derivative of the outside. 2 times something is 2. But then times the derivative of the inside is 3. So there's where you get the 6, and that's the chain rule. So we did the derivative of the outside as if it was just 2x. Derivative of the inside is 3, we get 6. And this is what we did right here. We did dy du. We pretended we were taking the derivative of 2 times something, or 2 times u is 2. And the derivative of u with respect to x would be 3. Well, if we multiply these two together, the du's would cancel out, and we'd end up with dy dx. Multiply those two together, you get 6. So they're all the same thing. They all end up with the same answer. So this one, I think that makes, I don't like example 1. I think it makes it more confusing than what it is. And I think example, I'll show you it. The polynomial y equals that is this squared, is a composite of u squared and 3x squared plus 1. So there's really something squared, and what's being squared is 3x squared plus 1, so it's a function within a function. The first one, that's just a polynomial, but we could turn it into the chain rule. We wouldn't want to do that, but we could. So dy du, the derivative of really the outside, which is the squared function, is 2u. Du dx, which is the derivative of the inside function, is 6x. But we know what u is. U is, where is it at? Where is u? Right here, 3x squared plus 1. So this is 2 times 3x squared plus 1 times 6x, because if you multiply these two together, you get dy dx. Hey, thank you. Elena. There you go. That never startles me. I'm a little dead inside, because never, not once ever in my life have I ever turned around and there's a person right here, I'm like, hey, how's it going? There's another math teacher, she said she jumps every single time. Not me. Oh, you're here to stab me? Okay, go ahead. I have no fear, I guess. Well, not of that. I don't think they're here to stab me. I was just like, if it was a threat, I'd be like, oh, how's it going? I'd be dead. No reaction. Any questions? That's not a great example of what we're doing. I like example 3. An object moves along the x-axis so that its position anytime t greater than or equals 0 is given by that. Find the velocity of the object as a function of t. So find the velocity. So in other words, take the derivative. So the outside function is cosine. So the derivative of cosine is sine, and we leave the inside alone. If this is too loud, you can go to the breakout area. If this is too loud, you can go to the breakout area. Okay. There's the derivative of the outside, and then we multiply times the derivative of the inside. So the only thing we can really do is maybe put it in a better order. 13 on. There it is. That's it. I don't like example 1 and 2. It makes it look more complicated than what it is. Outside inside rule. It sometimes helps to think about the chain rule this way. If y is f of g of x, in other words, a function inside a function, then y prime or dy dx is the derivative of the outside, leave the inside alone, times the derivative of the inside. That's what they're saying there. In other words, differentiate the outside and then the inside. Try example 4. See if you can get example 4. The outside function is sine, so derivative of sine is cosine. We leave the inside alone. You cannot do both derivatives in the same step. I'll show you that in a minute. Then times 2x plus 1. So there's the answer. Now we could rearrange it maybe a little bit. We could, yeah, I wouldn't do much with this. I'd leave it. Now over there on the caution, and I'll just kind of summarize the caution, it says that you can't do this. Cosine of 2x plus 1. That's not allowed. That's not how it works. Not that it's not allowed, it's just that's not the answer. You can't do both derivatives at the same time. It's like peeling an onion. You peel the outside layer, then you peel the inside layer, and then you peel the next layer. But every time you peel a layer, the onion inside stays the same. So that stays the same, and then you multiply times the derivative of the inside. You can't do them both at the same time. You can write it down, but it's wrong. Guarantee it's wrong. There are 3 inside functions here. The first one is tangent of something. Then the next function is 5 minus sine of something. And then the last function is 2t. So there's 1, 2, 3 function. This is a 3-layer function. So g prime of t is secant squared of 5 minus sine of 2t. There's the outside layer. The outside's tangent, derivative of secant squared. The next layer is 5 minus sine, which is negative cosine of 2t. And then finally, the innermost is 2t, and the derivative of that is 2. So that has 3 layers to it. There's the derivative. Power chain rule. This refers to the first thing that we did, example 1 and 2. This was in there. It's saying that the derivative of y with respect to x is the derivative of the outside function times the derivative of the inside function. And these are called differentials, and they cancel out. So you end up with dy dx on this. Okay, blah, blah, blah. I think that would be more confusing if I read that. We'll skip that. Letter A, find the slope of the line tangent to the curve at the point where x is pi over 3. Old question, new derivative. So part A, slope of the line tangent. So dy dx is the slope of the tangent line. And that's equal to, now when you have trig functions to a power, you should think of it like this. That's really the same thing. So sine to the 5th is sine to the 5th. Let's use the power rule, 5 sine of x to the 4th. So there's the power rule. We leave the inside alone. That's the whole theme. Derivative of the outside, leave the inside alone. And then now times the derivative of the inside, which is cosine of x. That's the derivative, but now we're just simply asking you to evaluate when x is pi over 3. So 5 times sine of pi over 3 to the 4th times cosine of pi over 3. Sine is square root of 3 over 2. Cosine is a half, so that's 5 times 9 over 16 times a half. So 45 over 32 is what I get. 45 over 32. B, show that the slope of every line tangent to the curve is positive. let's rewrite, well, first of all, this is y. Y equals 1 over 1 minus 2x to the third. That's the function there. I'm not going to use the quotient rule if the top is just a constant. I'm going to write this as 1 minus 2x to the negative third. That way I can use the power rule. So dy dx is equal to negative 3, 1 minus 2x to the negative 4. There's the power rule. Multiply by negative 3, reduce the power by 1, and then multiply by negative 2. That's the derivative of the inside. So then we have 6 over 1 minus 2x to the fourth. And I would say that the derivatives are always positive. This is always greater than 0 because anything raised to the fourth power is greater than 0. Something like that, if you're supposed to justify. Yeah, so all the slopes will be positive for that original function. Chain rule, chain rule, chain rule. You will miss this, hopefully not often. But if I said you're going to miss anything on this problem, you're going to miss that negative 2. And not only that, and I don't stand up here and claim that I'm perfect, I miss that too. That dang chain rule gets you a lot. So hopefully it doesn't. If it ever does, if you ever see me miss it up here on the board, just, hey, Mr. Smith, you forgot the chain rule. I would love it if you caught me missing that. I don't like missing it, but it'd be great if you caught me on it. I'd be like, good job, you thought of it. You will miss the chain rule at least once over the next couple months. Hopefully not. Prove me wrong. Please prove me wrong. That'd be great. Students will be able to find the derivative of a function using the chain rule. Find the first derivative of the function. Find the first derivative. Let's do the first one here. F prime of x is equal to 20 times 3x squared minus 2 to the fourth. So there's the power rule. And then we're going to multiply by 6x. So this one I would change to 120x, 3x squared minus 2 to the fourth. I'm pretty confident I can take 6 times 20 and not mess it up. And I'm not being sarcastic. I'm saying that equivalent forms are always accepted. I would take that risk. This one is 3x squared minus 5. The function is that to the 1/3. So I didn't do the derivative. I just changed what the function looks like. Change it to that because now you can use the power rule to find the derivative. So f prime of x is 1/3 3x squared minus 5 to the negative 2/3. So we reduce the power by 3/3 by 1. But then we have to multiply times 6x. And we do want to clean this up because later in the year, and not too far in the future, we'll be finding the zeros of derivatives. So that's 3x squared minus 5 squared. Not only will we find derivatives, not only find where it's 0, but where it's undefined also. Mins and maxes happen where first derivative is undefined or 0. So that's why we kind of clean that one up. 6 divided by 3 is 2. That's why I have 2 at the top. And yeah, then we work with radicals. F prime of x here is derivative of tangent is secant squared of 4x squared minus 5x plus 1. And then times the derivative of the outside is 8x minus 5. Now what I would not do, I took the derivative of all of the functions that appear in the original function. So I took the derivative of tangent, I can cross that off my list. I took the derivative of the inside function, I can cross that off my list, and there's nothing else to take the derivative of. And what I don't see very often, but every once in a while, is you'll take the derivative of that and write 8. This is not an original function. That is the result of taking the derivative. So you don't take the derivative of the derivative. That would be starting the process of the second derivative. So you just don't go forever with it. As soon as you take care of what's in the original, you're done. That's it. Don't go beyond that. Try the next one, please. You can help each other out. It's not a quiz. Think of this as secant of x to the 1/2 squared. That's really the way I look at this one. So the square root of x is x to the 1/2. Secant squared, that squared is really on the outside. So f prime of x is 2 times the secant of square root of x. And we would reduce that power by 1, but it's 1. So there's the derivative of the squared part. The derivative of secant is secant tangent. And the square root of x is on the inside, so we leave that alone. So derivative of secant is secant tangent. Leave the inside alone. And then finally, the derivative of x to the 1/2 would be 1/2 x to the negative 1/2. Now I would definitely clean this one up. 2 divided by 2 is 1. We have secant squared to the square root of x, tangent square root of x over square root of x. There we go. There's the final answer. All right, this one's a doozy, this next one. You ready? This one's a good one. First of all, on this one, we have the product of two functions. We have x and we have square root of 4 minus x. So this is the first one that we've seen that is a product of two functions. This is a composite. That's not multiplication other than the 4 times it. This is a function in a function. All of them are a function inside a function except for this one. This is the product of two functions. So we have to start out with the product rule. So we'll have first times the derivative of second plus second times the derivative of the first. So we have to fill that in. There's the product rule. So first times the derivative of the second. Now that's 4 minus x squared to the 1/2. That's the second function. So to take the derivative is 1/2, 4 minus x squared to the negative 1/2. So there's the power rule. Multiply by 1/2, reduce by 1, but then times negative 2x. So yeah, this is the product rule, but it has the chain rule built inside. You will always do the chain rule from here on out if it requires it. So first times derivative of second plus the second function is the radical, times the derivative of the first, which is just times 1. If we're going to try to find the 0 of this derivative, we have a lot of cleaning up to do. First of all, 2 divided by 2 is gone. We have negative x squared over square root of 4 minus x squared plus square root of 4 minus x squared. So there it is, somewhat cleaned up. No more negative powers. I did not lose the negative. That's good. X times x is x squared, and the 2's are gone. Well, if I'm going to find the 0 of this function, I got to get rid of the fact that we're adding two fractions together. Combine fractions. We do that by getting common denominator. Well, that's negative x squared plus 4 minus x squared over square root of 4 minus x squared over the common denominator. You square a square root, and the square root goes away. So 4 minus 2x squared over square root of 4 minus x squared. So the information that gives us that we'll try to talk about later is that the zeros, if you minus 4, divide by negative 2, and square root, so the zeros are at plus or minus square root of 2, and this function is the derivative is undefined at plus or minus 2. So plus and minus 2 make this undefined. We'll use that information later. But that's why we're going to combine in like terms. That's why we're going to add the two fractions together so that we can find the zeros and where this is undefined. This one, first of all, the square root of 1 is 1. and then we have the square root of x to the third minus 1. So I could do that. We can take the square root of the top and the bottom. That's legal in Nebraska. Then I can write this as x to the third minus 1 to the negative 1/2. So that's how I would change this function in order to just use the power rule rather than trying to use the quotient rule. Quotient rule would be a nightmare. So f prime of x is negative 1/2. X to the third minus 1 to the negative 1/2. So there's the power rule. That's the derivative of the outside. And then times the derivative of the inside is 3x squared. Well, not much cancels. We have negative 3x squared over 2 square root of x to the third minus 1. So now 0 of the function is 0. And this is undefined at 1. 1 to the third minus 1 is 0. Go ahead. Oh, yeah. Thank you. Yeah, I totally messed that up, didn't I? Good catch. That's awesome. Negative 3/2. I never minused 1. So that's negative 3x squared over the square root x to the third minus 1 to the third. If I had stickers, I'd give you one. I don't have any. Questions? Great catch. I should not have made that mistake, but I did. Should we try this one? Oh, yeah, this one's not that bad, really. Find the third derivative of that function. Can you find the third derivative? This becomes really important at the very end of we'll do this in March. We'll find third derivatives and fourth derivatives and fifth derivatives. First derivative times 2. So 8, 2x minus 1 to the third. There's the first derivative. You have to remember to multiply by 2, and that's kind of what we're checking here. Can you remember to multiply by 2? Second derivative, 24, 2x minus 1 squared. Oh, I almost forgot. Times 2, 48, 2x minus 1 squared. And you can see the numbers get pretty big pretty quick. So 96, 2x minus 1 times 2, which is 192 times 2x minus 1. So there's the third derivative. AP likes asking you questions on general functions, on functions that we don't know but we can get the value of, and that's where charts come in. So we have f of 3 is 5, f prime of 3 is 4, and so on. We don't know what the functions are, but we know what the values are. If h of x is f of x squared, find h prime of 5. So h prime of x is 2 times f of x. Reduce the power by 1, so it's really to the first power, but we wouldn't write that. So we reduce the power by 1, but then times the derivative of the inside function, which is f. So there's the chain rule right there. Derivative of the outside times the derivative of the inside. Now h prime of 5 is equal to 2 times, that's to the first power, f of 5, which is 8, and then times f prime of 5, which is 6. So let's see, 16 times 6, I'm looking at 96. Now, of course, I want you to get the value, but this is the important piece right there. If you can't get that, you're not going to be able to get the values. That's the important step right there. Derivative of the outside, leave the inside alone, times the derivative of the outside, or inside. Find the equation of the tangent line to the curve at the indicated point. There's the point. We need the slope. Old question, new derivative. Try to find the equation of the tangent line. I would write this as 2x, or think of it, I actually wouldn't write this. I think of it as that to the 1/2 power. So f prime of x is 1/2 2x squared plus 7 to the negative 1/2. See, I remembered that time. But then times 4x, times the derivative of the inside. So this becomes 2x over square root of 2x squared plus 7. There's the derivative. And we're evaluating this when x is equal to 3. So 6 over 9 times 2 is 18. 18 plus 7 is 25. 6/5. 6/5. So y minus 5 is equal to 6/5 times x minus 3. Any questions on this? With your partner, on the last part of it, on the last slide, I've given you the function, I've asked you to take the derivative, and I've given you the answer. So try to get the answers. I really would like to see you get these answers. And if you're watching this at home, don't look up here. Do not look up here. I'm going to flash this for if someone's watching this video. There we go. There's the work. You can pause, and I'm going to put this back up. Maybe I'm going to put this back up. How come it's not working? Oh, I don't want that. This.